You're sitting there right now, and light from the screen is hitting your eyes. That light traveled from the screen to your retina in about a billionth of a second. A billionth. And you didn't notice because it's just instant. As far as you can tell, the light leaves and arrives at the same moment, but it doesn't. There's a speed. Light has a speed, and that speed is the strangest, most fundamental thing in the entire universe. It's not just fast. It's not just the fastest thing there is. It's the speed that nothing else can reach. It's the cosmic speed limit, the maximum velocity for anything, anywhere, ever, 300,000 kilometers per second. That's how fast light moves through empty space. And I want you to really think about what that means. In 1 second, light travels far enough to circle the Earth 7.5 times. 7.5 times around the entire planet in the time it takes you to, say, one Mississippi. The moon is about 380,000 kilometers away. When you look at the moon, you're seeing it as it was a little over a second ago, not as it is now, as it was. The light had to travel all that distance, and even moving at 300,000 kilometers per second, it took time. The sun is 150 million kilometers away. 8 light minutes, we call it. When you look at the sun, and please don't actually look at the sun, but when you see it, you're seeing 8 minutes into the past. If the sun suddenly vanished right now, we wouldn't know for 8 minutes. We'd keep seeing it, keep feeling its warmth for 8 full minutes before the last bit of light reached us, and then nothing. The nearest star beyond the sun is 4 light years away. 4 years. The light you see from that star tonight left before you started reading this. If someone on a planet orbiting that star was looking back at Earth with a powerful enough telescope, they'd see Earth as it was 4 years ago. They'd be looking at the past, at ghosts, at light that's been traveling through empty space all that time. Now here's what should bother you. Why does light have this particular speed? Why 300,000 kilometers per second and not some other number? Why not twice as fast? Why not half? Nobody knows. I mean that. Nobody knows why the speed of light is what it is. We can measure it very precisely. We know it to 9 decimal places, but we can't explain it. It's just a fact about the universe, a number that nature picked, and we discovered it by doing experiments. Maxwell figured it out first, though he didn't realize what he'd found. He was working on electricity and magnetism, trying to understand how electric and magnetic fields behave. And when he wrote down the equations, when he worked out the mathematics, something peculiar appeared. The equations predicted that electromagnetic disturbances, waves of electricity and magnetism, would travel through space. And the equations told him exactly how fast they'd travel. He calculated the speed using things he could measure in a laboratory, the strength of electric forces and magnetic forces. And when he did the arithmetic, the answer came out to be the speed of light. That wasn't a coincidence. Light is an electromagnetic wave. It's electricity and magnetism oscillating together, traveling through space. When you see red light, you're seeing electromagnetic waves oscillating about 400 trillion times per second. Blue light oscillates faster, about 750 trillion times per second. Same phenomenon, just different frequencies. Radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, they're all the same thing. All electromagnetic radiation, all traveling at the same speed. The only difference is how fast they wiggle. But here's where it gets really strange. The speed of light is the same for everyone. No matter how fast you're moving, no matter which direction you're going, when you measure the speed of light, you always get the same answer. Always. Think about what that means. Suppose you're in a car going 100 kilometers per hour and someone throws a ball forward at 50 kilometers per hour. From the ground, that ball is moving at 150 kilometers per hour. Speeds add. That's common sense. But light doesn't work that way. If you're in a spaceship going half the speed of light and you shine a flashlight forward, you'd expect the light to be going 1.5 times the speed of light, right? Half from your motion plus 1 from the light itself. But no, someone sitting still watching you go by measures that light and finds it's going exactly the speed of light, not faster, the same. How is that possible? Einstein asked this question when he was 16. He imagined riding on a beam of light. What would you see? If you could catch up to light and ride alongside it, would it appear to be standing still? Would you see frozen electromagnetic waves hanging in space? But that didn't make sense. Maxwell's equations don't allow stationary electromagnetic waves. They only work if the waves are moving at the speed of light. So if you could ride alongside a light beam, you'd see something that violates the laws of physics, and that can't be right. Einstein realized the problem wasn't with light. The problem was with our assumptions about time and space. If the speed of light is the same for everyone, then time and space must be flexible. They must change depending on how fast you're moving. This is special relativity. When you move fast, time slows down. Not for you, you feel perfectly normal. But compared to someone who's not moving, your clocks run slow, your heartbeat slows, your aging slows. Everything about you proceeds at a slower rate. And space contracts. Distances shrink in the direction you're moving. A meter stick held forward gets shorter. Again, you don't notice. From your perspective, everything is fine, but someone watching you sees you compressed, flattened in the direction of motion. These aren't optical illusions. They're real physical effects. Time really does slow down. Space really does contract. And these effects get more and more extreme as you approach the speed of light. At 90% the speed of light, time runs at about half speed. A journey that takes 10 years for someone on Earth takes about 5 years for you. At 99% the speed of light, time runs at about 1/7 speed. 10 years becomes a year and a half. At 99.99% the speed of light, time runs at about 1/70th speed. 10 years becomes about 2 months. The closer you get to the speed of light, the more extreme the effects become. Time slows more and more. Distances shrink more and more. But you can never reach the speed of light. You can't. It's impossible. Here's why. As you go faster, you gain energy. Your kinetic energy increases. But in relativity, energy and mass are related. E equals mc squared. Energy is mass times the speed of light squared. So when you gain energy, you gain mass. Not much at ordinary speeds, but as you approach the speed of light, your mass increases dramatically. At 90% the speed of light, you're about twice as massive as when you're at rest. At 99%, you're about 7 times as massive. At 99.99%, you're about 70 times as massive. The closer you get to light speed, the more massive you become, which means it takes more force to accelerate you further. And as you approach light speed, your mass approaches infinity. It would take infinite energy to push you all the way to the speed of light. So you can't get there. Nothing with mass can. Only massless particles like photons can travel at the speed of light, and they have no choice. They're born moving at that speed, and they die moving at that speed. They can't slow down. They can't speed up. They just go. Now let me tell you something that seems impossible but is absolutely true. From a photon's perspective, if a photon could have a perspective, no time passes, ever. A photon leaves the surface of a star 1,000,000 light years away. It travels through space for 1,000,000 years by our clocks, and then it enters your eye. From our point of view, that's a 1,000,000-year journey. But from the photon's point of view, because of time dilation at light speed, the journey takes 0 time. The photon is created and absorbed in the same instant, in its own reference frame. And the distance it travels? Also 0. Length contraction at light speed compresses the entire 1,000,000 light years down to nothing. So the photon experiences no time and no distance. The universe, from a photon's perspective, is a single point in space and time where creation and destruction happen simultaneously. That's what it means to travel at the speed of light. Now, you might ask, what if we could go faster than light? What if there's some way around the limit? Well, there isn't. Not in any normal sense. The speed of light isn't just a speed limit for light. It's a limit for causality, for cause and effect itself. If you could send a signal faster than light, you could send information backwards in time, and that creates paradoxes. You could send a message to your past self telling yourself not to send the message. Does the message get sent or not? It can't both happen and not happen. The universe doesn't allow paradoxes, so it doesn't allow faster than light travel. But here's something interesting. The speed of light is only constant in a vacuum. When light enters a material like glass or water, it slows down. Not because the photons themselves slow down. Individual photons always travel at the speed of light. But in a material, photons get absorbed and re-emitted by atoms, and that process takes time. The effective speed, the average speed through the material, is slower. In water, light travels about 25% slower than in vacuum. In diamond, about 60% slower. And this slowing down, this change in speed when light enters a new material, is what causes refraction. Light bends at the boundary between air and water because it changes speed. And the amount of bending depends on how much the speed changes. When you put a straw in a glass of water and it looks broken, that's refraction. When a prism splits white light into a rainbow, that's refraction. Different colors slow down by different amounts in glass. Blue light slows more than red light, so they bend at different angles. Everything you see is light bending, reflecting, interfering, traveling from objects to your eyes. And all of it happens at the speed of light, or close to it if the light is passing through something. Now here's a question that puzzled people for a long time. How does light travel through empty space? Sound needs air to travel through. Ocean waves need water, but light crosses the vacuum of space with nothing to carry it. How? For a while, people thought there must be some invisible substance filling all of space, some medium that light waves propagate through. They called it the ether, and they did experiments trying to detect it. If Earth is moving through the ether, they reasoned, we should be able to measure that motion. Light should travel faster or slower, depending on which direction it's going through the ether. But every experiment failed. The speed of light was the same in every direction. No matter how carefully they looked, they couldn't find any evidence of the ether. Einstein explained why. There is no ether. Light doesn't need a medium. Electromagnetic waves are disturbances in the electromagnetic field, and the field exists everywhere, even in vacuum. Light propagates itself. Changing electric fields create changing magnetic fields, and changing magnetic fields create changing electric fields. The wave pulls itself forward through space at the speed of light. No medium needed, no ether required, just the field and its own dynamics. This was hard for people to accept. Waves without something to wave in. But that's how it is. Light is self-propagating. It carries itself through the emptiness. Let me tell you about something else that's peculiar. Light has momentum even though photons have no mass. In classical physics, momentum is mass times velocity. No mass means no momentum. But in relativity, momentum depends on energy too. And photons have energy. When light hits something, it pushes on it very gently. The pressure is tiny, but it's real. This is called radiation pressure, and it has effects. The tail of a comet points away from the sun, not because of the solar wind, though that contributes, but because of light pressure. Photons from the sun push on the dust particles in the comet's tail and drive them outward. You can build a solar sail, a huge reflective sheet, and use sunlight to push a spacecraft. No fuel needed, just photons bouncing off the sail, transferring momentum, accelerating the craft. Slowly, very slowly, but continuously. And in the future, we might use lasers to push spacecraft to high speeds. Beam intense laser light at a sail, and the momentum of those photons can accelerate the spacecraft to a significant fraction of light speed. Not all the way to light speed, but maybe 10% or 20%. Fast enough to reach the nearest stars in decades instead of millennia. That's all because light has momentum. Now let me tell you about the strangest consequence of the speed of light being finite. It means we see the universe in the past. Everything we look at, we see as it was, not as it is. You look at your hand. You're seeing it as it was a few nanoseconds ago. The light took time to travel from your hand to your eyes. You look across the room. You see the wall as it was a few nanoseconds ago. You look at a distant mountain. You see it as it was microseconds. You look at the moon. You see it as it was 1.3 seconds ago. The sun, 8 minutes ago. Jupiter, when it's closest, 33 minutes ago. Neptune, 4 hours ago. The nearest star, 4 years ago. The center of our galaxy, 27,000 years ago. When you look at the center of the Milky Way, you're seeing light that left when humans were still living in caves. The Andromeda Galaxy, 2.5 million years ago. Distant galaxies, billions of years ago. Some of the galaxies we observe are so far away that we're seeing them as they were when the universe was young. We're looking back in time, watching the early history of the cosmos. The most distant light we can detect is the cosmic microwave background, the afterglow of the Big Bang. That light has been traveling for 13.8 billion years. We're seeing the universe as it was 380,000 years after it began, not as it is now, as it was then. We cannot see the present. The present is inaccessible. We can only see the past. The farther we look, the farther back in time we see. This is what a finite speed of light means. Information takes time to arrive. Light takes time to travel. And that time delay means the universe is layered in time. Nearby things are recent past. Distant things are ancient past. There's another consequence. The universe has an edge, a horizon beyond which we cannot see. Not because there's nothing there, but because light from beyond that distance hasn't had time to reach us yet. The universe is about 13.8 billion years old. You might think that means we can see 13.8 billion light years in every direction. But the universe has been expanding. Space itself has been stretching. Light from distant galaxies has been traveling toward us, but space has been expanding the whole time, carrying those galaxies farther away, even as their light approaches us. When you work out the mathematics, the edge of the observable universe is about 46 billion light years away. That's the horizon. Beyond that, we cannot see, not because there's nothing there, but because there hasn't been enough time for light to reach us. And every second that horizon expands, more light arrives from slightly farther away. We see a little bit more of the universe, not much. The expansion is slow, but it's happening. Now I want to tell you about something that connects all of this together. The speed of light is not just a speed limit. It's a conversion factor between space and time. In relativity, space and time are not separate things. They're woven together into space-time. And the speed of light is what relates them. It tells you how much time corresponds to how much space. 1 second of time corresponds to 300,000 kilometers of space. That's what the speed of light means. It's the exchange rate. When physicists do relativity calculations, they often set the speed of light equal to 1. Not because it's actually 1, but because it simplifies the equations. If you measure time in seconds and distance in light seconds, then the speed of light is just 1 light second per second. The number disappears from the equations. And when you do this, something becomes clear. Time and space have the same units. They're the same kind of thing. The distinction between them is just a matter of perspective, of which direction you're looking in four-dimensional space-time. This is why time dilation and length contraction are related. They're two aspects of the same phenomenon, the rotation of space-time from one perspective to another. The speed of light is the thing that makes this rotation possible. It's the fundamental structure of space-time itself. So when I say the speed of light is the most important number in physics, I'm not exaggerating. It's not just how fast light goes. It's the relationship between space and time. It's the maximum speed of causality. It's the thing that prevents paradoxes. It's built into the fabric of reality at the deepest level. And we don't know why it has the value it does. We just know that it does. Nature picked this number, this particular speed, and everything else follows from it. You're made of atoms held together by electromagnetic forces, and those forces propagate at the speed of light. The light you see traveled from some source to your eyes at this speed. The thoughts in your brain depend on electrical signals moving through neurons, and those signals are ultimately limited by the speed of light. You are a creature living in a universe where this speed exists and shapes everything. You cannot escape it. You cannot exceed it. It defines the structure of space and time themselves. And every time you look at a star, you're seeing the past. Every time you turn on a light, you're creating electromagnetic waves that propagate at this cosmic speed limit. Every moment of your existence is governed by this fundamental constant of nature, 300,000 kilometers per second. That's the speed. That's the limit. That's the universe telling us something deep about how reality works. And we've barely scratched the surface of understanding why.